This thematic unit describes in more depth the methodology of the indicators related to thermal comfort, in particular those included in the climate change adaptation and air quality challenges. With their application, protocols designed to improve the ventilation of classrooms in winter and to take advantage of night cooling in summer can be introduced. It also includes those related to improving rainwater management. The monitoring period is determined by the installation and commissioning of the NBS, marking the beginning and end of the ex-ante and ex-post monitoring within the period studied. Indicators included in the climate change adaptation and mitigation and air quality challenges have been selected for their relationship with thermal comfort. The indicators of the water management challenge have been selected because of the importance of water management in Mediterranean areas. This unit will develop the methodology that has been established to calculate the impact of each indicator. First, the methodology for calculating the indicators of climate change adaptation and mitigation challenge will be explained. To calculate the impact of the NBS implemented in the school regarding the indoor temperature of the building, it is first necessary to find suitable locations for the sensors inside the classrooms. This assumes, however, that what really matters are the average value and the comparison between the values collected before and after the interventions. Also, a general consideration is to avoid locations close to doors and windows. It should be noted that air temperature is measured, not radiant temperature. In order to assess the temperature variations, a reference is taken, which can be the outside of the school or a classroom that is not affected by the interventions and in which no significant changes have been made. To numerically assess the impact of the actions, a simple calculation is to take the average monthly value or whatever period is considered, and compare it with that of the previous year both inside and outside the classroom. By assessing the percentage variation, the impact of the actions can be observed. It can be interesting to select the calculations data that corresponds to the daily school period. On the other hand, by analyzing the indoor and outdoor temperature profiles in summer, it is possible to establish the opening periods to take advantage of nighttime cooling. The building envelope temperature is measured using thermal images of the building envelope before and after interventions. It serves to visually show the impact of the interventions on the surface temperature of the building and can be used for communication purposes. Photographs are taken at least once before and after interventions under similar environmental conditions, preferably on days with high temperatures. For a correct measurement, the emissivity of the materials and the reflection temperature must be set in the thermal imaging camera. The reflection temperature must also be set, which is usually equal to the ambient temperature. Finally, nearby radiation sources that generate reflections and alter the actual thermal characteristics should be avoided. To assess the impact, thermal images taken before and after the interventions are compared, detecting possible changes in temperature ranges and decrease in maximum temperatures. It is also possible to compare the temperature of the surface affected by the nature-based solutions with other parts of the facade that has not been altered. In addition to the thermal images, at some points the indoor surface temperature and the near outdoor temperature of facades and roofs retrofitted with NBS are recorded to determine the thermal performance of the retrofitted envelope. Additionally, the air temperature inside classrooms is monitored to record the influence of these strategies on the indoor thermal environment. Through the comparison of the results, it is identified which of the variation of the technique is the most appropriate, considering that the main difference between them lie in the density and the height of the vegetation or in its configuration. Identical expressions are used to assess the impact of interventions on the exterior of the building as those used to assess the impact on the interior of the classrooms. Modeling the case studies makes it possible to forecast the effectiveness of the techniques to be incorporated, mainly in terms of comfort and energy demand. For the modeling, a preliminary analysis is carried out to find out, in general terms, how the climatic conditions affect the comfort inside the building and what strategies are proposed to improve its condition. The model is then fitted based on the information about the building and its environment, and a calibration is performed to increase the reliability of the forecast. The proposed techniques are modeled and incorporated into the initial model to form the model of an already refurbished building, and finally the simulation is carried out. It is estimated from the results the efficiency of the solutions used in terms of comfort and energy demand. The estimation of the heating savings is calculated on the basis of the energy consumption of the buildings before and after the interventions. This indicator is calculated using the actual annual fuel consumption data for each building. To select the baseline value, the average value of the last 10 years of the school activity is used if sufficient data is available. Apart from the building envelope conditions, other parameters such as outdoor temperatures or the management of the heating system can affect the consumption. To estimate the impact, the temperature profile during the winter months is also studied. Next, within the water management challenge, the methodology for calculating the rainwater management saving indicators will be explained. The second indicator refers to how the presence of the NBS influence in the capture and infiltration of rainwater. We have used the curve number method, which is a widely used method to calculate the runoff produced during rainfall events. This method is very interesting as it takes into account the following factors: the absorption capacity of surfaces and the behavior of the vegetation cover. The next factor to consider is the type of surface. For this, we will look at horizontal surfaces, their texture, and how rainwater infiltrates through them. The vegetation cover is also an active part of the rainwater infiltration processes. Here, we will consider two factors: the type of vegetation we have and the activity of the plants throughout the year. Although it could be necessary to carry out experiments to determine the real infiltration capacity of the installed vegetation cover, we can assume that we start from a bare soil in the previous situation, and after the actions, we move on to an intensive type of vegetation. To determine whether or not we are in the growth period, we can also estimate it with the meteorological data. In the graph, we can see an example that corresponds to the climodiagram of the area of Solana de los Barros. The graph shows rainfall in blue and temperature in orange. We can say approximately, and taking into account the species planted on the surfaces, that the growth period takes place in the month in which the temperature curve is above the precipitation curve, and the rest period the opposite is true. And finally, we consider rainfall. Here, we not only have to take into account the amount of water that falls, but also how long it has been since it last rained. The accumulated rainfall and temperatures will determine how the starting surfaces will be, drier or wetter. We start by obtaining the daily rainfall values for the period under consideration from the data of the nearest weather station. On rainy days, we add the precipitation of the previous 5 days. With these values, we determine the soil moisture condition. Using the table shown in the image and a spreadsheet to automate the operations, we can find out on each day of the period considered in what humidity condition our surface is in. Once we have the data, we calculate the surface runoff from the formula in the image, where I is the amount of rainfall fallen, and S is the maximum potential difference between the rainfall and the runoff generated, which is obtained from the curve number. The curve number can be obtained from tables or nomograms from literature. In our case, we have used tables from literature, which take into account vegetation type, soil type, and moisture conditions. Next, within the air quality challenge, the methodology for calculating the indoor carbon dioxide concentration levels indicator will be explained. To measure the concentrations of carbon dioxide inside the classroom, one sensor is placed per classroom, up to a total of about 5-6 classrooms. This indicator assesses the support that NBS can provide to the improvement of indoor air quality by facilitating ventilation operations and due to ventilation protocols. In summer, by reducing the temperature of the area around the building, classrooms can be ventilated, so less heat is introduced in the building. For the calculation of this indicator, a similar equation is used to those shown for the case of the variation of indoor temperature of the classroom. A direct application of the recording of CO2 concentration is the selection of the ventilation time periods necessary to keep the values within the recommended rates. The recording of the concentration values gives the time of day at which the values can reach high levels, and by combining these profiles with those of the outside temperature, the most suitable times for opening doors and windows and for how long can be found. This could be valid for both summer and winter, but of course with different times. In the case of automatically opening windows, their programming can be easily adapted from time to time. To assess the impact of the NBS on the perceived noise in the classrooms from the outside, a source of white noise of 80 decibels average is placed at 10 meters from the facade, and the noise inside the classroom is measured with the windows open and closed. This is not an indicator of great interest for this project because the solutions are not designed to reduce external noise. In general, the use of vegetation alone does not reduce noise significantly. Where necessary, vegetation has to be combined with other solutions such as noise barriers with appropriate designs to have an appreciable impact. To evaluate the impact, the reduction in percentage with the implementation of the solution in several classrooms of the school is assessed. Finally, I share in this slide my email address to answer possible questions and the direction of the communication channels of the project, such as the website, Twitter, LinkedIn, and YouTube. Thank you for your interest.
In collaboration with the LIFE program of the European Union.